So we're going to continue now from where we left off in the last lesson. Just at the end of this little section, I want you to be aware of particular examples of exo and endothermic reactions that you will come across. So you know that an exothermic reaction is going to be recognizable by the temperature of the surroundings increasing. So the obvious example there is any combustion reaction. So if you've got a match burning or a Bunsen burner burning or a gas cooktop or a bushfire burning, these are all combustion reactions and heat is released. So that's exothermic. Another common one that you're already familiar with are the neutralization reactions. And this is when an acid reacts with a base and the surroundings gets hotter. Endothermic reactions don't come across nearly so often. The most common one is the chemical cold pack, which many of us know is not particularly useful, but it's better than walking several miles to find a packet of peas in the freezer. So the chemical cold pack takes in heat from the surroundings because it's an endothermic reaction. So the products have a higher energy than the reactants. So that extra energy has to come from somewhere, and it's coming from the surroundings, making the surroundings colder. The other one that's really common is our changes of state. And changes of state, depending on which direction we're going, solid to liquid to gas or gas to liquid to solid, are exothermic or endothermic. So when we move from a solid to a liquid and a liquid to a gas, we have to take in energy for that change to occur. You can't melt ice without heating it. So those reactions taking in energy are endothermic. And the reverse processes, so gas condensing to form a liquid or a liquid freezing to form a solid, these are exothermic reactions. They give out energy. So that's the end of that first little section. So make sure you do the questions and try to get into the habit of writing down the 3 main points that you learned from this section. They don't have to be major. Now, I've got a nice little summary here of what you know so far about delta H. You have the definition that delta H is the enthalpy of the products minus the enthalpy of the reactants. According to this definition, then, if the temperature increases, we are seeing energy being given out, and the reason for that is the enthalpy of the products is less than the enthalpy of reactants. So there's leftover heat energy, so it's given out. If the temperature decreases, then our enthalpy of products is greater than the enthalpy of reactants. Energy has to be taken in to get up to that higher value for the enthalpy of the products. So that's your endothermic reaction. Now, how do we put this into a chemical equation and improve a chemical equation? So a chemical equation can be improved by adding information about the energy being released overall or being gained overall. And when we do that, the chemical equation becomes a thermochemical equation. So really important to make that distinction. And when you are asked for a thermochemical equation, you must make sure that the delta H term is at the end. Now, you will usually have a way to work out the value of delta H. If you don't know the value at all, then you might write something like delta H is negative, just delta H negative like that. That you might see that in the textbook as well. So in this case, we have the combustion of methane. And this equation is telling us now, the thermochemical equation, when 1 mole, and we're actually going to take it literally now. We're not saying a 1-to-2 ratio. We are literally saying when 1 mole of methane reacts with 2 mole of oxygen, we produce 1 mole of carbon dioxide, 2 mole of water, and 890 kilojoules of energy is released. So that negative value there is code for is released. So you don't read it as a negative energy, you say the energy is released. Now, the reason for this literalness, I guess that's a word, is that the delta H is being calculated from the enthalpy being absorbed when the reactant bonds are broken and the enthalpy released when the products are made, as per this absolutely riveting animation, which I could watch all day. So what we have is energy going in to the reactants, breaking their bonds. We get up to the highest energy point, the activation energy, and then energy is released and we go down to the products. Now this is, actually no, I'm giving you a minute. What sort of reaction is this? Exothermic or endothermic? All right, that was your minute. This is an endothermic reaction because the enthalpy of the products is greater than the enthalpy of the reactants. So you'll see we don't get as much energy given out again as we had to put in to make it happen. So the more reactants and products we have, because we're dependent on the actual amounts, the more bonds there are that we're going to be broken, the more bonds are going to be made. And so the difference between the enthalpy of the products and the enthalpy of the reactants will increase. So delta H will increase when amounts of products and reactants increases. Now, for those of you who like to see numerical examples, I've just made up some numbers here. So if we've got a fictitious reaction in which the energy that has to go in to break the reactant bonds is positive, is 200 kilojoules, and the energy that's released when the product bonds are formed is 600, then overall the delta H is negative 400 kilojoules. Now, if we double the amount of reactants, then the energy put in to break double that amount of reactants will be 400 kilojoules. The energy released when the products are formed is 1200 kilojoules. The difference is 800. So you'll see that delta H has doubled when the amounts of reactants and therefore products has doubled. So we can write this information as a thermochemical equation. So you've got your straightforward thermochemical equation for methane reacting with 2 mole of oxygen, etc., etc. If we double all the amounts, then delta H is doubled. So now delta H is negative 1,780 kilojoules per mole. That per mole terminology is a little bit interesting. We tend to say that the per mole here is, so per mole is for the amounts shown in the equation. So it's not, as every other per mole would be, it's not for 1 mole, it's for the amounts shown in the equation. So 890 does happen to go with 1 mole of methane, but you could say it also goes with 2 moles of oxygen. Here, the 1780 matches the 2 mole of methane. If we halve our amount of methane from the original equation, we get half a mole of methane reacting with 1 mole of oxygen, making half a mole of carbon dioxide, 1 mole of water, and 445 kilojoules of energy is released. Now, if you reverse that reaction, it becomes endothermic. As it happens, the reverse reaction really doesn't occur. It's not spontaneous. You just can't make, well, not easily anyway, you can't make carbon dioxide and water turn into methane and oxygen. That's clever stuff, which we don't go into. But if you just happen to write that equation in the reverse, it would be endothermic. You'd have the same number as the original number of moles, the 890, but now it's going to be positive. What about states? Well, states are important. We all love living in Victoria. Right, pause for laughter. Haha. So you will know that in Unit 2, we could write the equation for the evaporation of water. And we said that water in the liquid state turns into water in the gaseous state. And delta H for that reaction is endothermic, because you've got to put energy in to make something evaporate, and it's 44 kilojoules per mole. So 1 mole of water in this case needs 44 kilojoules of energy to change into gas. So if we take that knowledge and apply it to our thermochemical equations, then we have to realize that if the delta H for methane making liquid water is 890 kilojoules per mole, being exothermic, then if for some reason you wrote it with a gaseous symbol, we'd have to take this equation here into account. And so we'd drop our delta H value by 44. Actually, no, 2 lots of 44, sorry, 88, because there's 2 mole of water made. And what you could translate that as 2 mole of water is made, and then 88 kilojoules of energy is put in to change it into a gas. Now, the other very important standard here is that we use the liquid state. So the liquid state is used because that is the state at room temperature under standard conditions, 25 degrees. So the states we write in our equations, unless we're otherwise told, are the states at room temperature, and then we don't have to worry about whether we've got the delta H right. Activation energy, this has already been referred to a little bit. Let's just talk more about it. It will also come up when we do our kinetics later in this unit. The definition initially is that activation energy is the amount of energy required to break the bonds of the reactants. From this energy, go away. From that energy up to that little peak. And you'll sometimes hear that activation energy referred to as the activation energy barrier. It has to be met, overcome, before the products can be formed. So it's the amount of energy needed to start a reaction. That's a little bit of a colloquial way of putting it. This red one is your definition. So we're talking about the spark needed to start a fire, the spark needed to burn the fuel in an internal combustion engine, all sorts of things like that. Some reactions have such low activation energies that they just start on their own, what we might call spontaneous combustion. Glad I'm not facing you now and facing questions about whether spontaneous combustion even occurs, because I don't know. So we are looking at activation energy being added to the reactants, and we get a high energy complex being formed. It has a name. It's called the transition state. Will you be asked about that in Year 12 exams? No, you will not. As we go past that high energy state, we're always going to be releasing energy. It's just a matter of how much energy is released as to whether that reaction is exo or endothermic. What about catalysts? Well, catalysts provide an alternative reaction pathway. So they provide another way for the reaction to go ahead. And you'll see when we do rates of reaction that a catalyst is a good way to increase the rate of reaction. Doesn't happen for all reactions because not all reactions have catalysts. The point about this alternative energy pathway for the reaction that makes it increase the rate of reaction is that the pathway has a lower activation energy than the original reaction. So you can see in this energy profile diagram, here's our uncatalyzed reaction going right up to this value here, EA, right up there, whereas the catalyzed reaction has a much lower activation energy. So it's a really clever way to make a reaction increase its rate. And you can directly relate it to the energy required to break the reactant bonds. So here's an exam question from June 2007, when I'm pretty sure you were all still alive. You were probably only one or two, but never mind. Fun fact, my year 7s were mostly born in 2010. So anyway, this example is a multiple choice and it's asking you to look at a two-step process. Now, it's really saying take the information you already know and put it together into a new situation, because no one expects you to have come across a two-step process before. So our two steps are A plus B turning into X, and that's got a positive delta H, so it's endothermic. So if I was reading this question, I'd be annotating it like I am now to make sure that I was keeping track of what's going on. And then X, which is the same X as that X, right? X is turning into C, and that's exothermic, negative delta H. So at this point, before I even look at the alternatives, I might draw myself a little energy profile for those two processes. So the energy profile for an endothermic reaction is low to high. It doesn't matter that that's a bit pointy. And this is X. And so that's step 1. And then step 2, I'd say to myself, well, that's exothermic, so that's high going down to low. So I've got my X and I've got my C. So now I need to put that information together to match the alternatives. So I need to start off low, and the end of that first stage is higher. So A is already out because X is lower than A and B. And so is C because it was just slightly lower. So B and D are still in the race. Now, you will find with lots and lots of Year 12 multiple choices that you can quickly get down to a 50-50 chance. So don't worry about 4 alternatives. You'll quickly get down to 2. So now we're focusing on the second stage, and we know that being an exothermic reaction, we want C to be lower than X. So that leads us to alternative D being the right answer. So that's the end of this section, which I think basically equates to section 2.2. So do the questions on page 45. If you need more explanation, try watching the Volk Science videos. Otherwise, move on to the next video.